Hey guys, thanks for tuning into CMTEQ channel. So a while ago I made a tutorial on tricky diode forward and reverse bias circuit, and a few days ago I just followed it up with some in-depth explanation on how each one of these circuit, as you can see here, are actually forward or either forward or reverse bias. So if you haven't watched that tutorial, please you have to do a little catch up on that one. Now in this particular tutorial, as you can see, I've got a bunch of resistors and I've got a diode here, basically two diodes, but I'm only going to use one of them because we only have a single diode in each one of these circuits. So the purpose of this one here is to basically prove in each one of these cases what we were able to find. So I will tell you already, we say that this one here is reverse biased and all the rest of them are forward biased. Right now, so that was just to find out, right? To find out whether it is indeed reverse or forward, because we know that the rules say that in order for a diode to be forward biased, the anode need to be more positive than the cathode, then the current will go through, right? And vice versa, then it will be reverse biased, right? But now, if you now move into a practical model or an ideal model of a diode, where we know that in an ideal model, there will not be a voltage drop across this diode in a forward bias situation, right? It will forward bias, ignore the 0.7 volt across it for it to conduct. So that's 0 volt drop on an ideal diode. But on a practical model diode, as you can see here, right, a practical model will have a small internal resistance inside the diode. Now that internal resistance will dissipate some heat depending on how much current you are pushing through the diode, right? And that current will drop a voltage plus the forward voltage drop of the diode. That's going to give you a combined voltage drop. Like this particular diode here, so this is a 1N5408, right? A general purpose rectifier diode. Basically this is a power diode because it can conduct up to 3 amps according to the data sheet. 3 amps with a maximum forward voltage of about 1.2 volt, right? So if you are sinking 3 amps of current through this diode, it will drop about 1.2 volt. So you need to take account of that. That 1.2 volt is like its waste, it's gone. You're not gonna have that voltage. Okay, now having said that, let's move into the first circuit here. So the first circuit, what do we have? We've got a 5 volt power supply, we've got a 10 ohm and a 8 volt power supply, which is connected in the opposite direction. So I've got my power supply already ready here. So this particular one here I can measure. Let's just do this way. So you can see that we've got a 5 volt. Okay, so this is our 5 volt, and on these two exposed wire here that you can see, I've got the 8 volt here. Let's just confirm that. There we go. It's about 8.3 volt. Right. So now we are able to get to about 8.2 volt. Okay. So we leave it at that. So we've got a 5 volt and we have a 8 volt. All right. So this is the 8 volt power supply. And below here, we've got a 5 volt power supply. There it is. So we've got a 10 ohm resistor. So I'm going to connect the one end of a 10 ohm resistor to the anode of my diode. So I'm going to need a little bit of press sticks here so we can construct our circuit. Right. So we just need to thin this a little. Then we will connect the 10 ohm. Okay. So now the next thing here is to, obviously, we need to connect the power supply. So this power supply here, we know that this one is giving us a 5 volt. So the positive supply of the 5 volt must be connected here. The negative of the power supply here must connect to the negative of this power supply here, so that they're going to form a common ground. So basically we are connecting two power supplies in series here. Okay, so we've got a negative of that power supply connected to the negative of the other power supply. What is left here is basically just to connect the cathode of the diode to the side of the circuit. Alright, so now it's time to turn on the power supply. There we go. So the power supplies are on. We need to do some basic measurement here. Let me just take off these press sticks here. Now, when we were doing the theory of these bias circuit, on this number A, we say that there was a -3 volt here. Because if you run the loop, you will realize that there will be a subtraction of power supplies voltages, so there will be a -3 volt present here. So that made this diode not to be forward bias, but instead reverse bias. So I'm going to confirm it by measuring the voltage across the diode. There we go. So we are measuring -3.2 volt. -3.2 volt, that's the voltage dropping across these diodes. So that means the diode is reverse bias. Now we know that a reverse bias diode means there is no current flowing across it. So I'm going to disconnect here, and I want to connect an ammeter in series so that I can be able to basically measure the current flowing through the circuit if there is any current. So I cut off the circuit. So I've cut off the circuit and I've placed my multimeter in between the diode, cathode, and the 8 volt power supply. Okay, so now I place my multimeter on an amp reading. Now we can turn on the power supply again and we monitor. So you can basically see there is no current flowing. We don't have any current flowing there. We can still measure the 3.2 volt, the negative 3.2, and there is no current flowing. So effectively the diode is reverse bias. Right, now we move to the next one. Now this next one, we were able to determine that this diode here is indeed forward bias. Now the only problem to practically prove this is we need a 100 volt DC power supply, which I do not have. Okay, so but we however have a resistor 560. I think I have something around 670 ohm, right? So we have a resistor, we have a diode. Now we don't have a 100 volt DC power supply. Now I'm going to do a small trick here, which I do not recommend for anyone to do it at home. So I'm going to use a variable transformer that I have here, and I'm going to connect a bridge rectifier, a full wave bridge rectifier, and tune the RMS voltage up until I get about 100 volt DC on the output, and use that to test this particular diode, which is going to make this next experiment a little bit dangerous. So not recommended if you do not know what you are doing. Right, so I've got the variable isolated transformer here. Now we just need to do some basics connection here. First I just need to connect the output onto this output socket here so I can get my voltage out. Then these just need to be on the press sticks here. They must not go anywhere because this is alternative current AC voltage, so it's dangerous. So please do not attempt this if you're not sure of what you're doing. Now if I probe, obviously I'm not gonna get anything here. Orientation doesn't matter, it's AC, so there is 0 there. If I turn it on, now you can see I'm getting about 62. I'm getting about 62 volt AC here. Okay, So let me turn it off. Okay, so I've got a bridge rectifier here with a capacitor already connected it. Now this combo here will give you quite a very smooth DC output without ripple, but obviously you're going to get ripple either way when you start drawing current out of it. But the only problem here is this capacitor here is a 35 volt, so this is not going to work for the 100 volt. So I have to take off this cap. Unfortunately, I don't have a 100 volt capacitor available with me here, so all I'm going to do is just basically to use it without a filtering or a smoothing capacitor. Right, now I have a capacitor removed, and then I've got my bridge rectifier here. So as you can see that the two pins here are the minus and the positive, and the two at the back are the input AC signal. So I'm going to put my AC input right here like that. So I'm not gonna solder anything. This is basically a makeshift circuit going on here. Okay, now if it's off, so I'm going to turn it on again. Okay, now if I measure here, you can see I'm getting the same 63. I'm not sure if you are able to see. We still have the same 63 volt AC. Now if I measure here on the output DC side, so obviously you can see I'm getting about 18 volt AC, and this is just because of a high unfiltered output. And now if I change it to the DC, and we should be able to measure, there we go. So I'm measuring a 60 volt DC because my probe are reversed, so I was measuring a negative one. So let's go this way. So we can see that we're getting 64 volt DC. So it is a high voltage DC. Now what I'm going to do, obviously I only have two hands. I'm going to turn it off, and I'm going to take these probes. Okay, and I'm going to connect this way. Okay, right, now I'm going to turn my variable transformer on again. And what are we getting here? We're getting a negative 60 volt. My probes are reversed again. Okay, let's do it this way. Okay, there we go. So we've got 60 volt here. Now I'm going to increase my output here with my variac all the way so I can get to 100 volt DC. There we go. So now I've got 100 volt unfiltered DC power supply. So I'll turn it off. Okay, now we know that we've got 100 volt on the terminal of this bridge rectifier. Now we know we've got 100 volt here. This is my negative, right? So this is my negative where my cathode must be connected, and the positive, that's where I'm going to have my 560 ohm resistor connected. So let me just construct the circuit. Okay, so this is case number 2. So we've got our 100 volt power supply. The circuit is constructed. I've got my 670 ohm resistor. Okay, then we've got a diode cathode. You can see it's connected to the negative of the 100 volt, as you can see, and the positive of the 100 volt is going to the resistor. So I just broke the circuit so I can measure the current with this ammeter, right? And then I've also got probes to measure the voltage across the diode. Okay, so here we go. I'm going to put this briefly. Then we're going to monitor the current that's going to flow through. That proves that indeed the circuit is being forward biased, and the voltage across the diode. Okay, we know that for an ideal diode, the voltage across it will be 0 when it's conducting, but this is not ideal. This is a real world silicon, so 0.7 volt must drop. But for a practical complete model, okay, so we know that there will be an internal resistance, so that also will make that a diode will drop some voltage, so that will combine. So we're going to read more than 0.7 volt. Depending on how much current we're pushing through, that voltage can also keep going up. And earlier I said that for this diode it can go all the way up to 1.2 volt. Now here we go. Let me turn this on and then we start monitoring. Now we can see we're getting 146 milliamps. The voltage across here is 7.73. Now the resistor is smoking. Now the resistor was smoking, and which means this resistor is suffering here, is actually bearing the consequences of what's going on here. Now why is the resistor smoking? Obviously because there is too much power across that resistor. Now if I measure this resistor now, and I am guaranteed that is no longer what we measured it earlier, okay, I'm getting 652 ohm, which means for some reason the resistor is still okay. The resistor is still okay, it's not damaged yet. Okay, so what I'm gonna do is I want to measure the voltage across this particular resistor. Let's measure the voltage across it, and we know how much current will be flowing across it, and we know what power in terms of the power dissipated across a component. That will mean the voltage across it times the current crossing that particular resistor. That will mean the power that's being dissipated across that particular resistor. Okay, so I'm going to change this to voltage, and let's get the critical reading here. So I'm gonna turn this thing on again. Here we go, 146 watt. Now I'm getting negative. Okay, my probe must just be reversed. My probe must just be reversed here. Okay, there we go. And I will turn it on again. So it's 90 volt across that resistor and 150 milliamps, so it's smoking. So you can clearly see, right? So what's happening here is we're feeding in 100 volt. We're feeding in 100 volt. Okay, now the 100 volt was an open voltage that we measured. There was no current flowing through. So which basically means when there is some current flowing through, that 100 volt will actually going to drop across the diode inside the bridge rectifier. So effectively we're going to be getting about 90 something volt, right? So depending on the calculations there, so what happened is out of the 90 something volt, 0.7 is dropping here, less than the voltage is dropping here, then the rest of the voltage are sitting here across this resistor. Okay, across this resistor we just measured now here that we are reading, here it is again, about 91 volt. Okay, so we're getting 91 volt across a resistor at 150 milliamps. There it is at 148 milliamps, 91 volt. Now you can work out that power, how much it is. So if I just take my calculator here, so 91 times 0.15, that is about 13.6 watt. That's 13.6 watts. So what it means here is this resistor here is not suitable for this circuit. That's why it's suffering. So you need a resistor that is able to take 13 watt or more. Actually you need a 20 watt resistor here so it can breed. Otherwise you need to spec your circuit by changing this resistor so you can limit the amount of current that is going to go through. So if you limit the amount of current, that basically also you are limiting the amount of power that's going to dissipate across it. So let's say you limit this current to about 10 milliamps. There it is. So if you limit it to about 10 milliamps, you're going to get about 0.9 watts. That's about 1 watt. So basically a resistor like this, which is a 2 watt resistor, will be able to sustain it. So you need a big resistance value so you can limit the current to about 10 milliamps or 20 milliamps, something like that. Then you will have a 2 watt resistor will be able to stand in your circuit. Otherwise you're going to have smoke and your circuit will get damaged in a matter of time. So this is it for this experiment of option 2. Now I'm going to move on to this option here. So that's option C, where we've got a 30 volt power supply and we've got a 1K instead with a 1.5 kilo ohm and a 4.7 and another 4.7. And we've got the diode. So we say that this particular diode was also forward bias. So we just need to also prove that. All right, so we are on to the next one. I just want to do some resistor measurement here. So this is the first one. So this is a 1K resistor. As you can see there, it's 1K. Then the next resistor here is a 1.5K. Now I could have just put a 1 resistor 2.5 kilo ohm for simplicity. Then the next resistor going down to ground is a 4.7K. As you can see, 4.7K. Then the next one to the diode is also a 4.7 kilo ohm. So now what I need to do here, take my diode, connect the anode of it onto the resistor like this, and then connect these points together and tie my ground. And then we are done with our circuit. Then we can move on into testing. Okay guys, so this is not a prettiest looking circuit. Before I turn everything on here, I want to ensure that we get a voltage that is not 100 volt. We need a voltage that is 30 volt. Okay, so I need to go down here. Now I only have 2 hands here, 80. So let's keep going, maybe a little more, 47. All right, so 30.6 volt. Now we're getting 30.6 volt. Let's turn it off. Now what I'm going to do, instead of connecting a wire here, I'm going to connect my ammeter so that I can measure the current that is going to go through this circuit. So let's, this is, like I said, this is not a pretty looking circuit here, but we just want to prove that our diode is indeed forward bias. Okay, this one just need to come back like that. All right, okay, so now when I was explaining the theory of the circuit, we say that for this diode to be forward bias, we're going to have a voltage at this point, at a voltage divider point, and that voltage is then going to push a current through this way, and there will be some voltage drop across here, the 4.7K, and we'll have a voltage drop across the diode, right? And because that voltage is greater than the ground level here, then the diode is forward bias. Now we're just going to prove that by also measuring the voltage across the diode. Then we'll see that it will be definitely must be more than 0.7, because this is a complete model application here. So now I'm going to turn this thing on. Hopefully we're not going to get a smoke, because I haven't done all the mathematics of power dissipation here. Now we're getting about 4.5 milliamps of current. So that means this diode is forward bias. Now I'm going to measure the voltage across it. As you can see there. Right. So now when I measure, I'm getting about 0.5 volt. So this is very much interesting. I'm getting about 0.5 volt, not 0.7 volt, but it is indeed forward bias. So the voltage across the resistor, the 4.7 resistor there, it's about 10 volt. I am on the way here. Let's see, put it this way. Okay, so that's about 10 volt across this resistor. Okay, across this diode, that's about 0.5 volt. Okay, so the point is have been proven. So practically we're getting less than 0.7, but indeed the diode is forward bias. Then let's move on to the next one, and that will be the last case here. Okay guys, we are now on the last case here. Now we also say that this particular diode is forward biased. Upon doing the mathematics of this case, we found out that there was a negative 5 volt here, because each one of these resistors had a 15 volt across it, and the minus 20 volt here was then summing up, subtracting and giving us a negative 5 volt. Now because the cathode was at negative 5 volt, that means the anode was more positive and this diode was forward bias. Now let me turn on the power supplies here. So now this is the negative 20 volt that I've connected. So that's a negative side, that's a positive side. You can see the cathode of the diode, the resistor, and the anode of the diode is on the positive side of the 20 volt. And on this side I've got the 10 volt power supply. So I've got the resistor, and the negative side is connected to the anode of the diode with this probe here, so that I can be able to measure the current. They are connected. Okay, so let's go ahead and turn on the power supplies. Now I'm not sure if I can be able to measure the power supply here. Okay, there we go. You can see there is 10.8 volt there. Then let's turn on the other power supply, and that one we said it must be 20 volt. So we need 20 volt. Okay, how much are we able to get if I measure across this way? Okay, I'm getting about 19 volt on this power supply. But now the point here is to prove that the diode was indeed forward bias. Now let's measure. Now the current, you can see, is 1.2 milliamps of current, so that basically means the diode is forward bias. There is some current flowing. Now if I measure across the diode here, you can see I'm getting 0.5 volt. So that basically means this diode is indeed forward bias, because I am able to measure the voltage drop across it, which is positive. So the diode is indeed forward bias. So this is it for this tutorial. If you found anything helpful, please don't forget to subscribe to CMTEQ channel and give this tutorial a thumbs up. Until next time, stay tuned for more tutorial like this. Cheers.